Now, let's say we got an example where we got inside temperature and an outside temperature, and we measured the temperature gradient. Uh, so the inside temperature here, T infinity 1 is 20 degree. When temperature of the inside wall uh, is a little bit less, like here. Oh, sorry, that was not supposed to be 20. The difference is 20. The gradient difference from T1 to T2 is 150, and the difference, the T infinity 2, the difference between that and T2 is 30 degree. Now, the total rate of heat transfer, which is joules per second, which is also known as watt, is, let's say, 10 watt. So if we have a look at that one, we can express that in another word. We got Q dot, which is a rate of transfer of heat, U A delta T, where delta T is a change in temperature, A is the area, but the U is the overall heat transfer coefficient. It's a heat transfer coefficient. It is not the resistivity coefficient. The bigger the area, the lower the resistance. Yep. So here UA is going to be constant. The area of this wall is constant. It is not changing. Yeah. And the overall coefficient is not changing. Why? Because the inside air is not changing, and we assume the outside air is not changing. If it's a dry air, it's going to be dry air. If it's a wet air, it's going to be have the same humidity content. It is not changing. So we can write that thing as UA is 1 over R total. Once we got this one, we can rephrase the question. We can write down Q equals to delta T over R total. But remember, U is the overall heat transfer coefficient. Temperature drop. The temperature drop across a layer is proportional to its thermal resistance. The higher the thermal resistance, the lower the temperature drop. Lower the thermal resistance, higher the temperature drop. In the previous one, if you have a look at between T infinity 1 and T1, and also look at T infinity 1 and T1. Yep. Now, if you have a look at that one, R convection is a convection happening. So R convection is actually 1 over H1A. So this is the inside of the wall. If I want to look at the outside of the wall, it's going to be R, convection outside. Let's call it R2. This is R1, sorry, R2 is 1 over H2A. The area remains the same, so I can just put that one there. Or I can just put it like this. So in question, this is 1, 2, 3, 4. Out of these 4 things, one thing will be missing, and you need to use the formula to find that one thing, yeah, by rearranging the equation. Now, multi-layer plane walls. If there is many layers of the wall which are connected in series, what we do is we add the total resistance. We actually add the total resistance. Yep. Imagine there is I will show you the next picture. Imagine there is a wall. There is a wall 1 and there is another wall 2. Imagine these two walls are made of different material. This wall is made of material 1. This wall is made of material 2. So it has different K. So this is a K1, which is a conductivity coefficient, and this wall has another conductivity coefficient. If we just look at the graph, the rate, the slope is, the gradient is high, like it's more slopey, which means this one, K2, has a high conductivity, and this one has a low conductivity. Yeah. Ideally, for a proper insulation or 100% insulation, we want a wall like that, so we don't want anything to happen. Yeah, but that only happen if we have the massive thickness of a wall, or if we use a material with a very high thermal resistivity. Yeah. Okay. Now for the convection, for this part, convection is happening. So for the convection, we write R convection 1 over H1A. For this part, the conduction is happening, and conduction, we have an equation R wall conduction L1, which is the L1 is this one, thickness of the wall, over K1A, where K1 is conductivity coefficient and A is the area. Then we use the same for the second wall, L2 K2A. And then here, convection is happening. So when we look, this side is convection, and this side is convection. And the rate depends on the temperature gradient. And between these two, it's all conduction. So we got all the R's. I can add all the R's to find out a 1 R total. So I can come up with an equation. This is the initial temperature, and that's the final temperature. So T infinity 1 minus T infinity 2 divided by R total. R total, I have to add all the R's together equal to the heat transfer coefficient. Okay. Now, if I zoom in, if I want to find the T1, now what is T1? This is the T1. If I want to find the T1, I have to use this equation. I have to just deal with the convection, the first part, T infinity 1 minus T1 over R convection 1. I need to get all the values except the T1. I will start with this temperature, whatever the value of this temperature is. Yep. I will have the convection coefficient because I can measure the area of the wall. I know the H value, and I know this one as well, so I can find this missing temperature. If I want to find the T2, where is T2? T2 is here. Now I find the T1. I got the T1. Now I need to find the T2. Yeah. To find the T2, what I'm going to do is I can do two different ways. I need to find out the and I have the T alpha 1, let's say T infinity 1, and T2 is missing. But I already find the convection coefficient inside of the wall and the thermal conductivity coefficient of the wall. How I can find that one? I have the area and I have the value of the K, so I can find this thing. To finding the T3, which is this value, finding the T3, I need the T3 minus T alpha 2. So I can, rather going from this side, I will go from this side. So outside temperature, I know the value of the outside temperature of the wall. I can measure it. T3 is the missing one. Convection, for the convection, I got the H value, and I know also got the A value. So I can just put that one in and I can find the missing bits. Okay, now we do one example. Heat loss through a wall. Imagine we are we got a wall of certain thickness, and the wall has a thickness of 0.3 meter. The inside temperature is given as 16 degrees centigrade. The outside temperature is given as 2 degrees centigrade. The area of the wall is 5 times 3. So that will give me the area of the wall. So first I need to find the area of the wall. I got the thickness of the wall. The K, conductivity coefficient of the wall, is also given 0.9 watt per meter Kelvin. I do not need to convert these thing in Kelvin if I'm just making that change. Yeah. So I can do that one. Let me just rub it. So we got the T1 as 16, and T2 as 2 degrees centigrade. Yep. Okay. We need to find out the rate of heat loss through the wall on that specific day. Now, you need to make sure you do mention the assumptions. Assumptions are extremely important. Now, when we look into this question, the heat transfer through the wall is steady since the surface temperature remain constant at all across the surface. So if you're looking at the surface, anywhere inside of the wall, you will have the same temperature. Anywhere outside of the wall, you will have the same temperature. Yep. Okay. And the temperature is one directional. Thermal conductivity, the value of the K is constant throughout, which is 0.9. Okay. We have the area, which is 15 meters square. We will use this equation Q equals Ka T1 minus T2 over L, where L is the thickness. Yep. We put the value. The value for the K is 0.9. Area is 15 meters square. I don't have to convert into Kelvin because even if I do, temperature difference will be same. T1 16, T2 2 divided by the L thickness 0.3, and that will give me the value for the Q. The Q is heat. Units are joules, but Q dot is joules over second. That is watt. Yep, 630 watts, and that's the answer. Yep. So you can get the answer straight away like that, rather going through R of a wall. Yep. Okay. Any questions so far? We don't need to. We don't need. I didn't find the thermal resistivity. I didn't find the resistivity at all. So this thing, because it's a simple wall, this step can be neglected. You don't need to use this step. Straight away get that one and put the answer. But if that's a multi-layer, maybe then this will come handy.